Hello and welcome back. We're going to pick up where we left off last time, and that is in looking at operations. Do you remember my definition for what an operation is in mathematics? Well, here it is for you. It's a procedure that produces a new output value from one or more input values. Okay? And we started to look at some operations. The most basic operation, we're going to get a formal definition this time. That's addition, right? What do you think the operation for addition really is? What does it mean? Well, I've given two definitions. Fundamentally, addition is the most basic operation because that's kind of where math started, right? If we're talking about the very beginnings of, even before we had written notation, if I have this quantity, whether I represent that using hash marks or Roman numerals or Babylonian or Sumatran numerals, Sumerian numerals, going back into history, that's the quantity 3, right? That number, the specific quantity is 3. If I get 2 more, I count 1, 2, 3, 4, 5, right? And we could start over. I had 1, 2, 3 for the green. And now once I get a couple more, I can start again and count 1, 2, 3, 4, 5. But it's a lot easier, instead of having to start over from 0, if I start with those 3 and then just keep on going 4, 5, right? If you have little brothers and sisters or cousins, or maybe you work at a preschool, this is a big step when students are learning their numbers, right? My youngest is right at this stage, right around now, right? When we're trying to do 3 plus 2, he starts over again, 1, 2, 3, 4, 5. He doesn't just start at the 3 and go 4, 5, right? But eventually, like my other children, he'll get that shortcut where he can just continue to count. And that's what we mean by addition. When we say 3 plus 2 more, I don't start 1, 2, 1, 2, 3. I go 1, 2, 3, and then another one, and then another one. And that's where I'm getting to 5. Now we can see that with dots, but that doesn't really work so well once we get past whole numbers. Right now, numbers started as whole numbers, counting things, but we need to be able to measure as well. Right? What does it mean to continue to count another 3/5 or the square root of 7? Right? That doesn't really fit this definition. So even though this is technically correct, I have another definition that's a little more precise. And addition means continue to move a specified amount in a specified direction. So that's where the number line really comes in handy. If I've got 3 to start with, I can think of that not as 3 dots, but as a distance of 3. Right, so I'm counting here 1, 2, 3. Go 1, 2, 3 to arrive here, or just move in a straight line to 3. Right? So if I'm adding 2 more, that means I'm continuing to move in this growing direction, in this positive direction. This distance of 2, right? That 2 moving forward, instead of starting over at 0, just like with counting, instead of starting over 1, 2, 3, 4, 5, I've gone 3, and then I'm continuing on 4, 5, right? So this distance of 3, continuing to move move how far? This specified amount, in this case, 2. I've gone 2 beyond where I started. 2 beyond 3 arrives at 5, right? And that's how we know the sum is 5. And there I've just slipped in another vocabulary word here. The word sum doesn't mean answer. The word sum specifically means the output value from the operation of addition. Right? Remember, an operation is a procedure that produces a new output value, right? So here's our output value, 5. We call that the sum. That output value is the sum of these two input values. And those input values also get a name. If we're talking about addition, we call those the terms. So make sure you write those down. Now, another word for this is addends. Right, so if you're in grade school or you're preparing to teach grade school, you may have been taught, let's use a new color here. If we have A plus B equals T, I like to use T for total, S for sum. S kind of looks like a 5, so I'll use T for the total, right? We call these the addends. But once we get into algebra, we don't really use this word much anymore. So some teachers like that word. I'm not a big fan. Once we get into algebra, we refer to them as terms. So we'll talk about like terms in a little while. So we call these the terms. And then this thing over here is the sum. Right? So addition means we continue to move a specified amount in a specified direction. Usually when we talk about addition, we talk about these two different terms. And so we call addition a binary operation, right? You need two terms in order to add. If I asked you, what's the sum of 5? You can't do anything with that, right? That would mean like 5 plus what, right? The sum of 5 and 3 is 8. Or you could write that out. The sum of 5 and 3. So here are my two input values separated by an and, is 8, right? So is, there's my equal sign, has the same value as 8. Right? Or you could say the sum of 1 and 4 is 5. But I'm not saying the sum of 5, I'm saying the sum of two other things is 5. Again, I can show that on the number line. Now, the number line doesn't always have to be nice and straight with all the numbers written out. Often when we're talking about sums, it's helpful to just show, okay, 1 going forward, 1, 2, 3, 4, past that. So the total, 1, 2, 3, 4, 5. That's how I get 5, right? That's using the number line. Same thing here, 5 and 3. So I got 1, 2, 3, 4, 5, plus 3 more, 6, 7, 8. I don't have to write in the numbers. I'm still showing these arrows moving, showing that I'm continuing to move. That's going to be really useful when we get into adding fractions, or particularly adding signed numbers. Once our specified direction, right? Addition, move a specified amount in a specified direction. So long as everything's positive, that direction is only forwards, only to the positive infinity direction. But hopefully you've seen negative numbers sometime before in your life. that's where direction can change. And once we get beyond the basic algebra, we get into adding vectors and multiple dimensions, this definition still holds even when our direction could be at various angles in the plane or in 3 space and so on. So you don't have to understand vectors in this class, but this definition for addition is robust throughout any element, no matter how complex you get. So that's the one you need to remember, right? This is true in certain contexts, and historically that's where we started, but this is the one that we really are going to use moving forward. Get it moving forward. All right. So that's addition, sum, and terms, describing the parts of addition. And I've used this next definition a few times already without specifying it, and that is the word equal. Equal doesn't mean the answer. Equal means has the same value, or have the same value, depending on what it is we're describing, right? So equal without an S is an adjective. Maybe I should specify that here. Adjective, right? I can say this expression, A plus B, is equal to this expression, T. They both have the same value. That's what this symbol is telling me, right? So that's where we need the verb in that sentence, is, or if we're more precise, we could say is equal to. But if we replace the verb is, or the verb phrase is equal to, with the single word equals, then our definition has to slightly change. So I guess with the adjective, we'll have to make that have, right? Two things are equal if they have the same value. And if we say equals, that's now a verb where we say has the same value as. And then we get into subject and object, right? So you can say the expression 5 plus 3 equals the expression 8. This subject equals this object. And because it works the same way both ways, 8 is equal to 5 plus 3. 8 equals 5 plus 3. So generally when we're saying these things, our subject is the longer expression and our object is usually a single value. But we could definitely be correct if we say something like 3 plus 2 has the same value as 4 plus 1. Right? 3 plus 2 equals, that looks like a Y. 3 plus 2 equals 4 plus 1. 3 plus 2 is equal to 4 plus 1. How do we know this? Because 3 plus 2 is 5, and 4 plus 1 is also 5. 5 equals 5. Right? All of these things are equal to each other. But when we just use equals by itself as a verb, that implies, just through our standard usage, that whatever is coming after that is going to be a single value, not an expression with multiple things inside it there. Okay. Now I've already given another definition, used another word that I have to define, right? And that is expression. Let me actually put that to a new page here. An expression is a meaningful collection of numbers, variables, operations, and or grouping symbols, no Y in grouping. And that's to be distinguished from an equation, which is a mathematical statement that two expressions have the same value. Right? Remember, equal means have the same value. So when we see the word equation, we should be seeing equa as part of that. Right? So an equation is going to have an equal sign in it. Right? Saying this expression has the same value as this other expression. And what are those expressions? There's some collection of numbers, variables, operations, and or grouping symbols that's meaningful in some way. So when I write 4 plus 1, what's in that expression? Well, I've got some numbers here, and I've got an operation. And I can understand what that means. The sum of 4 and 1. Okay, there's an expression. Equals over here, I've got a 4 plus divided. I've got a number, okay. I've got some operations, great. What does it mean to say the sum of 4 and divided? This is not meaningful. So it is therefore not an expression. That's not really a definition, but I'm going to give that to you for free. These 3 dots in a triangle is shorthand for therefore. I use that a lot in mathematics to say, based on what we already know, therefore we can make this next statement. Okay. But our expression could be simpler than this. I could say 4 plus 1 equals 5. Five has a number, great, so there's an expression. I understand the meaning of this expression. This is an equation. I could say 4 plus 1 equals x. There's a variable, great. I could say x divided by 3. Okay, I understand what that means. It's the, we'll get into explaining these other operations in future videos, but hopefully we recognize that. This could be super complicated. I could have grouping symbols here. Right? Whatever you want to do, if you understand the syntax and you understand these operations, we can make sense of what's going on here. If that's equal to some other expression, there we go, right? Here's an equation. That doesn't mean I know how to solve the equation. That doesn't mean you'll learn how to solve an equation this complicated in this class. But we can recognize that this is an equation because this is an expression. I've got some variables and operations and it's arranged in a meaningful way. And this is supposed to be a parentheses here. I don't know what happened there. This other thing is also meaningful. Now, if I mess up my grouping symbols, now this isn't meaningful anymore. I've got a bracket here that doesn't have any starting bracket to coincide with it. This is now messing up. This doesn't make sense anymore. So when you're writing your expressions, you have to be careful. Is what you're writing a true expression? Is it meaningful? Or have you missed some parts of it and now it's just kind of a weird something like this, not making sense? So we've got through a bunch of definitions today. I think we will get into other definitions and statements and proofs in our next video.